Hello, everyone. Welcome to the latest Hear from the Experts webinar. We'd like to thank our sponsor, Novartis, for providing education grants to make this session possible, through a variety of information videos and sessions like today. The Hear from the Experts webinar helps people better understand MS and provides tools to navigate their MS journey with more knowledge and confidence. Our intention is to help you learn more about the disease, wellness strategies, and much more. My name is Karina Montiliano, and I am pleased to be your moderator for this event. I would like to welcome and introduce our guest speaker, Dr. Paul Stys. He's a neurologist, a basic neuroscientist, and a leader in the study of pathophysiological mechanisms of white matter injury. He completed his neurology training at the University of Toronto, followed by a postdoctoral fellowship at Yale University. His lab studies disease mechanisms with a focus on MS and Alzheimer's, two diseases that may have a lot more in common than previously thought. How's that for suspense? Thank you so much for volunteering your time with us, Dr. Stys. I'm going to now hand it over to you because we're all patiently waiting to hear what you have to say to us.
Thanks very much for that kind introduction. If you can confirm for me that you can hear me and see my slides. All good? Okay, fantastic. Well, thanks again. So I'm going to spend not too much time, but 30 minutes or so, giving you an overview of what we think MS is, and some information that's come up in recent years about that may challenge our conventional thoughts about MS, and hence my title, Rethinking MS, because there's a lot of information that's coming up that may alter our thinking, and I think that's a good thing because we need new approaches, and therefore those new approaches and new thinking should spur some new solutions for patients with MS. So the talk is roughly divided into these four parts. I'm going to give you an overview of the traditional definitions and the traditional understanding of the disease. I'm going to give you some brief examples of some data points that have come up that kind of challenge our traditional thinking about MS, what I call flying the ointment. And it's these things that 10 years ago got me thinking about other approaches and another kind of avenue to approach this disease. In my lab, in my thinking about it. And I will show you some results from our lab as well. It will not be heavy on science because that's not the point here, but hopefully it will give you a flavor of the kinds of things that we do and some of the exciting new discoveries that we and others have found in our labs. And I'll end by kind of arguing about what the real disease really might be and the implications that that has for new therapeutics coming down the road, which I think are very important, especially for progressive disease. And it seems that the main interest from the poll is in progressive disease. So if you Google MS, I got this from Wikipedia, trying to find out what the disease is all about. I'm not going to read this whole definition. You can read it yourselves, of course. But a couple of key points come up. First of all, it's an inflammatory disease. It's aimed at the myelin sheaths. These are the coverings, the insulation around nerve axons in the brain and spinal cord that are essential for normal impulse transmission and therefore neurological functioning. That's the myelin. The immune system, of course, figures very prominently in the definitions and in our understanding of MS, as the conventional thinking is that the immune system is what starts everything with an immune attack against the nervous system, against the white matter of the nervous system, which is the collection of the nerve fibers in the brain and spinal cord. But importantly, 10 years ago, I got this definition, cause remains unknown. Unfortunately, that's still true today. We still don't know what causes MS, but I hope by the end of the talk, you'll agree with me that we've made some strides in trying to understand what this disease is all about. So now as a medical student a very long time ago, this is kind of what was taught in the classroom, and it's still taught today. And the idea starts with that there is a problem with the immune system in our periphery that is outside the brain. For some reason, these aberrant or misfunctioning immune cells are recruited into the brain where they attack the brain tissue, cause inflammation, cause loss of myelin. And those are the inflammatory relapses that most people with MS begin with. And that damage accumulates over time, and then this chronic inflammation with the damage that's been ongoing for years, in fact decades, ends up leading to progressive disease. So that's the kind of general, traditional, conventional teaching and thinking about MS that we've had for, well, really decades, and it's true today. And if that's true, if we develop anti-inflammatory medications that combat this immune attack, we should be in very good shape to treat all phases of MS. But as I'll show you, and as I'm sure you know, that's really not the case, and has not been, unfortunately, has not been the experience in the therapeutic world. So what is white matter? It's about 50% of the brain and spinal cord, and here's an MRI of a human person, and the white matter is this light stuff over here under the gray cortex, and it's all the connection of nerve fibers and myelin that connect all the nerve cells, and we have hundreds of billions of these in our brains that really do a marvelous job at connecting all the circuitry and making it work very well. Here, if you zoom in with a microscope, this is what an axon, so the axon is the nerve fiber that we're talking about. That's what it looks like. So every nerve cell in the brain has a single axon that comes out, and that's the output. That's where the information leaves the nerve cell to go and connect with the next neighboring nerve cell, and that's how the whole circuitry works. There are two key components of axons. It's the nerve fiber, or the wire itself in blue, and around it, it is the insulation, the myelin, and that's the key point in MS. It is the myelin that appears to be the major target for damage in MS. And like with any wire in your house or in your stereo, if you strip the insulation from a wire, the wire stops working and the signals stop conducting, and that's the problem in MS as well. Now, nerve fibers have a tremendously difficult job. They're tiny, and if you took an average nerve fiber that, say, goes from the top of your brain down to the bottom of your spinal cord, and if you expanded its diameter to the size of a 4-lane highway like the Trans-Canada, the length of that fiber would extend from one coast to the other of this country. So this is actually, this picture is an underrepresentation of just how complex and vulnerable these long nerve fibers are. Because the point is, if there's a breach at any single point along this nerve fiber anywhere, it's out of commission. The circuit, the impulses won't conduct, and that nerve cell is basically taken out of the circuit. And you strip one piece of myelin from this nerve fiber anywhere along this path, very long path, that fiber is taken out of the circuit. And that's a huge problem. And this is what happens. So there's a variety of diseases that cause trouble with myelin and the axon. So the axon wire is shown here, the myelin is shown here, but MS is very, very peculiar that it really tends to go after the myelin insulation. So two things go terribly wrong when this happens. First of all, the conduction of electrical signals is impaired, so they can't get from one end to the other. And the second really important thing that we've learned in the last few years is that the myelin provides a protective sheath around the nerve fiber, around the axon. It provides energy, it provides trophic molecules, which means basically it feeds the axon essential molecules to keep it healthy and alive throughout, 80, 85 years of a person's life. The one key point about nerve fibers in the brain is that they never regenerate. Once they are damaged, they cannot grow back, unlike, a liver or another organ. So this single nerve fiber that you're born with has to be kept healthy and happy for 85 years and functioning. And when the myelin is taken away, very often the nerve fiber itself suffers and undergoes what's called transection. It's basically cut in half. And once that happens, as I showed in the previous slide, nerve impulses cannot get through, and this will never heal in the human nervous system, unfortunately. So we really have to be very, very careful and very clever in keeping the myelin and the nerve fibers healthy and keeping the nerve fiber from being cut and damaged. So here's what does MS look like clinically? You're probably quite aware about the different phases of MS. You have your pre-symptomatic MS, that once you have your first attack, and that's probably true with any degenerative disease like Alzheimer's, Parkinson's, and others, that once you present with symptoms of the disease, you've probably had it for quite a while. So this doesn't happen at the first attack. Something's been going on for years, possibly even longer, and that's called the pre-symptomatic phase. And that's, of course, very difficult to detect because the person is perfectly healthy, has no symptoms, and unless you did some very detailed investigations like special MRI scans, you wouldn't really know that anything's going wrong. People present with what's called a clinically isolated syndrome, so the first attack. And at this point, something goes wrong. You have a symptom, usually comes and goes. And at this point, it's not clear if this is MS or just a single attack of something that will never come back. Most people with MS present with the relapsing-remitting phase, as you know, where there are clinical relapses. You get symptoms, a variety of neurological problems that typically come, and then they remit. And that's relapsing remitting. And this is due to inflammation that comes in waves, and it may come very frequently or very infrequently, or some people have a couple of these and never have anything again. So really the variety is all over the map, and it's really hard to predict who's going to do what in the next year, 5 or 10. And then often, but again, not in all, but often after a little while, this relapsing remitting phase transitions into a secondary progressive phase. So what happens here is that the immune system kind of peters out and stops attacking the nervous system repeatedly, and what you're left with is just a progressive decline in neurological function and an increase in symptoms without this fluctuation. Some people present with progressive MS from the beginning. Basically, I personally think it's the same underlying disease, except they simply did not have the earlier inflammatory relapses. But the important point is the blue line here. What we now think is that regardless of what kind of MS you have or present with, if you turn the clock back and go way back, probably even into adolescence, we now think that this disease began very, very early and has been very, very slowly progressive over time and continues to progress slowly in most patients. This rate of progression, of course, is different. Some people get into trouble very quickly. Others progress very slowly and really have few deficits until late ages. But really the key message here is this progression, this degeneration has probably been going on for a long, long time. And so here's an MRI scan of a patient taken once every week for a year. And what you see here is these white spots coming and going, and these are recurrent waves of this inflammation in a relapsing and remitting MS patient. Now, why do I show this? So, of course, most patients do not have such an active picture of MS. This patient, unfortunately, did. But the reason I show this video is to illustrate the fact that even if you don't have a clinical relapse or a manifestation, there's probably ongoing inflammation going on in the brain. And this inflammation is not good. There's a lot of molecules that are released during an inflammatory attack that leave in their wake a permanent small amount of damage to the nerve fibers and the myelin. That's why it's very important if you have active inflammation is to combat it, because in the end that will serve the patient well when he or she if they do enter the progressive phase. Because if you suppressed a lot of the inflammation in earlier years, you will have a lot more healthy nerve fibers to carry you through. And later on, as time progresses, again, in some but not all patients, you get atrophy. And that just means a progressive shrinkage of the brain. And this looks a lot more like degenerative disorders like Alzheimer's, Parkinson's, and many others. And I'll come back to that. So here in the progressive phases, inflammation is there, but it is certainly not as active as it was in the previous phases. And what you have instead, and this is the same patient scanned over many years by MRI, you can see the black parts are the ventricles, the fluid-filled spaces. They get bigger because the brain has gotten smaller and the nerve fibers basically have gradually degenerated and shrunken away. And this is the major challenge in the field. We really have, well, first of all, we don't understand why this happens. And second, we have very few treatment options for this. So this degenerative phase is the big challenge in the field that many of us are currently working on. So why did we as a research and clinical community focus so strongly on the immune system that we think goes about damaging the brain, and therefore has propelled development of virtually every single therapeutic we have available for MS patients. Well, it's understandable why this is. And look at the dates here. We go back to the mid-19th century in the days of Charcot, who was a brilliant French neurologist and one of the first who actually described MS as a clinical entity. And even way back then in the primitive microscopes, we had pictures of these nerve fibers that were damaged, that were cut, the myelin sheath was stripped. So we knew 150 years ago that this was happening. And to this day, we actually don't know exactly why. But what we do know now is this. So this is a blood vessel, this pink thing in the middle. The dark spots around it is a very heavy infiltration of immune cells, lymphocytes mainly. And so we see this over and over and over when we look at the brains of MS patients. So it's very natural to say, aha, something happened, the immune system rushed in, it's attacking the brain around blood vessels and causing damage to myelin and nerve fibers around this. So because we see this picture over and over, this was the natural conclusion and has basically defined the course of MS research and MS treatments for the last 3 or more decades. But the fly in the ointment that I mentioned in my first slide. So here's one problem. So when I looked at this literature and everything that we know about MS 10 or more years ago, you come across papers like this from a group in Australia, and they looked at some MS brain samples, and what they found was something very interesting. So while you see this inflammation in the majority of MS patients, the occasional patient exhibits the following. So the blue here is a stain for myelin. So all this area should be nice and blue. And here's a large MS lesion that's not blue. And that means the myelin has gone away, has been destroyed. And that's called demyelination. That's you're very familiar with. So if this is a big demyelinated area where the myelin was lost, and if the inflammation and the immune cells are always responsible for this, we should always see immune cells in lesions like this. But in this case, we didn't. There's actually almost no immune cells in this lesion over here, raising question that could you sometimes have typical MS lesions where there are very few infiltrating immune cells. And if that's true, and it appears to be, then that means that not all MS lesions are actually driven by an infiltration of toxic immune cells. And it kind of upends our entire thinking about immune cells being the primary drivers of this disease. So this raised questions in my mind. Here's a paper that I co-authored this summer with some folks at a large pharmaceutical company who have a very large MRI data set looking at many patients over many years. And this is a composite MRI scan where the heat map and the colors show your highest chance of developing an MS lesion. And what came out of this that's very interesting. The highest probability by far, shown in the red parts, is in areas adjacent to these fluid-filled CSF spaces. So CSF is the cerebrospinal fluid. It's the fluid that circulates around and within our brains. And when you see patterns like this, it raises a very important question. That is there something circulating around that's produced and released into the spinal fluid that circulates around and causes this toxicity and therefore lesions to form where we now know they form with much greater probability. And this has nothing to do with immune cells. This is some mysterious factor or toxin that's circulating around the spinal fluid that is causing secondary damage to the white matter in the areas shown. Again, very little to do with immune cells because they're not the ones that are circulating around. I'm not going to go through all these diseases, but I put this slide up as an example of autoimmune inflammation. So when you read this, and I'm sure many of you have, it means immune cells come first, inflammation comes second, and brain damage comes third. But here is a variety of examples of diseases that are genetic. That is, there are gene defects that cause damage to myelin, not because of autoimmunity, but because of biochemical defects to myelin. And I put this slide up to illustrate the point. When you look at the pathology, the MRIs, and the biochemistry of these patients, they all can look very much like MS. they have secondary infiltration of immune cells. They have oligoclonal bands in their spinal fluid and so on and so forth. Here, we know for sure that the primary problem was a gene problem of myelin, and everything else that looks like MS came secondarily, came after. So it really turns the horse and cart around, that you can have a secondary autoimmune reaction as a result of some very well-known primary problem. And we tested this directly in an animal model that I'll just run through very quickly. Many of you are familiar with EAE. So this is a model where you give some myelin fragment and you immune boost a mouse, and that mouse mounts an immune response against its myelin that looks very much like MS. And every single drug that's been developed for MS has been developed using this model. And therefore, this model is very successful for the inflammation in MS. But then we asked the question, can you get the same problem without giving an external myelin fragment? Can we generate internal myelin fragments, which is really, if you think about it, much more likely to happen in a patient with MS, that there may be an internal problem in the nervous system that, coupled with an immune boost, should lead to a lesion, an inflammatory demyelinating lesion like you see in MS? And the answer is yes. So we did this using this molecule called cuprizone. You give the mouse cuprizone for a very brief period of time, and that very subtly damages the myelin without any myelin breakdown, but it biochemically alters the myelin. And this is an MRI scan of the mouse, and this is the pathology. So what you find, if you just perturb the myelin just a wee bit, if you give an immune boost, just like the EAE people do, and then you wait a couple of weeks, you do the MRI scan, you can see the main white matter tract over here in dark, which is nice and healthy, is gone here. And the pathology shows all these tons and tons of these infiltrating immune cells, like I showed you in that picture from an MS brain with all those immune cells around the blood vessel. So this recapitulates very nicely what we see in real MS lesions without having any external myelin problems. All the myelin problems were generated internally, which we think recapitulates and is much closer to the real situation in the human. And this cartoon kind of summarizes the problem so that if you immune boost the animal with healthy myelin, nothing happens. But if you have just slightly unhealthy myelin, that is enough to trigger the immune system to react, and then you upregulate the immune system, then you get a big, huge inflammatory reaction with lots of damage to myelin, lots of damage to the axons, and lots of infiltration of immune cells. This lesion looks exactly what you see in a plaque from a human MS patient. And of course, there's the treatments, right? You're all very, I'm sure, familiar with these. We've now had over 2 decades of very successful treatment with anti-inflammatory agents. They're very good at combating relapses and inflammatory activity in the MS brain. But unfortunately, as you probably all well know, they are by and large rather ineffective in the progressive phase. So even after all this effort and all these drugs that are available, basically the adage that if you have no inflammatory activity on your MRI or clinically with relapses, you really have very little benefit with these anti-inflammatory agents. So that is, like I said, the major problem and the major challenge. So when you put all this together, it spurred me to write this opinion paper that we wrote close to 10 years ago now, challenging the field to look at things differently, challenging the seemingly accepted question, is MS really an autoimmune disease? Well, it is, of course, because the data are there. The autoimmunity and inflammation play a major role. The really important question, is it a primary autoimmune disease? That is, does an immune defect start the whole thing? Or does something else start the problem? And the autoimmunity kind of follows suit, as it often does in the nervous system. And then you get this vicious cycle. So most people think that autoimmunity is at the root. We and a few others think that chronic degeneration of the brain, like in Alzheimer's, really lies at the root. And our lab has spent the last 10 years working on this and testing this hypothesis to see if we're right or not. Because if we are, it will really overturn our understanding. And importantly, will usher in a whole new a whole new era of MS therapies for patients, especially in the progressive phase. So really, the question in my mind is MS really more like all the other degenerative diseases that we know very well? Alzheimer's, Parkinson's, probably well known to all of you. We hear a lot about these very traditional, conventional neurodegenerative disorders. There are many others, and we wonder whether MS will join this list or should join this list. Is MS like all of these, that it starts early with a degeneration, but is unique, separate from all the others, because it has a very brisk and prominent inflammatory relapsing flavor on top of that, which really confounds our understanding of things and perhaps distracts from the root cause of what the disease really is. This is still a question mark today. We and others are working hard to answer this question, but when I see data coming out of our lab and others, with every passing year, I'm becoming more and more convinced that MS really does belong in this list of degenerative diseases. So I'm coming to the end of my talk, and of course, you all want to hear about what's in the future for treatment for this disease, because naturally that is our collective goal, is to give better options and better the lives of MS patients, particularly those with progressive disease. So as I'm sure you know, there's about 20 currently available drugs, but virtually all of them are aimed at relapsing-remitting inflammatory disease. There are very few, they're coming, but there are very few options for progressive MS, and ironically, that's the biggest remaining challenge. Based on the data that I've shown you, that I did not have time to show you from our lab and a number of other labs, we now have a better understanding of what might be causing the progression in MS. And based on that, there's a number of interesting options that are coming down the road. Some inhibitors of enzymes that may be related to the deposits I showed you on the previous slide. And in fact, I'm involved with a biotech company in Toronto that, based on one of the papers I showed you a few slides ago, we are developing a drug that inhibits one of the enzymes that we think causes damage to myelin in progressive MS. So that's very exciting. It's a very different approach. This drug has nothing to do with inflammatory change or autoimmunity. It's a direct inhibitor of the enzymes we think are front row in driving degeneration of myelin. If MS is an amyloid disease like Alzheimer's, we could model our efforts on what's going on in the Alzheimer's field, for example, where there are a number of anti-amyloid antibodies that seem to at least clear amyloid from the brain on PET scans. Of course, if we better understand how this amyloid or other factors are damaging cells, we can better design protective drugs against cells, the myelin, the axons, the nerve cells. If you don't understand how things work and what damages cells, it's very hard to propose and develop drugs for those. I didn't have time to talk about the Epstein-Barr virus. This virus, which most of us get, seems to be essential for promoting MS. So basically, if you've never been infected with EBV, you cannot get MS. So there's some very mysterious but important connection between EBV and MS. We don't understand it. We're actually working on that as well as a side project. If we understand that connection better, perhaps drugs or vaccines directed at this virus rather than other things, the immune system or even other things shown up here, could be the very first step in what triggers the disease, probably in childhood, and we could have a chance of slowing, stopping, or even preventing it altogether. And of course, boosting repair. There are many, many efforts going on to try to boost myelin production and myelin repair in the face of ongoing toxicity and ongoing degeneration. So based on emerging data, the future of MS therapy is very bright indeed, I would argue, simply because we've solved the problem of inflammation, I think. But now we're starting to unravel the mysteries of what might be underlying and driving the inflammatory process upstream of the inflammation and the relapses. So there's lots of opportunities and lots of very interesting avenues that are being pursued. So very exciting to field to be in, and I look forward to more therapeutic options. I wanted to throw this one in because This is a plaque that my wife made for me that I hang in the office. And anytime students come to me and say, this is really hard, or this isn't going to work, or what are you thinking? Nobody's thought of this before. I kind of point to the plaque and say, it's easy to go down the road where everybody else has traveled. You'll probably find the same thing, but that's not the point. The point is to go down a road where no one has traveled, where it's hard, but where you may actually stumble on and develop something and discover something truly, truly different. And that's been kind of the mantra of our lab. We don't do the easy stuff. That's all been done already. We do the hard stuff, almost the impossible stuff. And some of the projects we do certainly qualify for this. And I really like this quote because every time I get kind of bummed out about things not working, I look at the plaque and I say, yeah, well, that's what you signed up for. So just continue on. So my last slide, I'm going to thank all the people that have worked very hard in the lab over the years to generate some very interesting and I think transformative data. Of course, we don't work alone. We work with a whole variety of very smart people around the world, the institutions that support us, and the funding. And I want to spend a minute talking about this. I can tell you from very personal experience that thinking differently and actually tackling the seemingly impossible has been very, very difficult over the years. It's actually quite easy to propose things that have been already proposed and largely done, do variations on the theme. It's actually very difficult to go down a road where people don't believe you and something's very different. We've seen many examples of this in science and medicine over the decades. So we've had trouble getting funding for our projects, and I'm very grateful to these agencies that took a chance on our very out and left field ideas, particularly philanthropic support. Were it not for philanthropy, these ideas and projects and insights that I could show you today, these projects would have died years ago, and I think it's very important to take a chance on things that are different, because you never know. Different thinking is what gets us different results and new observations. So we're very, very grateful for philanthropic support that has helped us along the years, and hopefully we'll come up with some very new ideas that will eventually translate into new therapies. So this is my last slide, so I'm going to stop here. I thank you for your attention and for hearing me out. Hope you found it interesting, and I think we have time for Q&A now.
I know there was a lot of stuff that came out of this that I had no idea about, and I think that's the prevailing thinking when it comes to MS is, as much as we know, we don't know. So I'd like to thank you on behalf of myself and everybody here for doing the work that you do and that your team does, and helping to be able to make a statement such as the future is very bright. So we appreciate that immensely. So on that note, as you mentioned, we do have some time for questions. One thing I'm going to mention is that we did have some questions that came in pre-presentation, and then as we requested, there have been some questions that have been coming through via both the Facebook and the Zoom chat. We will, of course, get to as many as possible, but of course, time is always of an issue, and we want to make sure that we don't keep Dr. Stys too far away from his research that is helping us ever so much. One thing that I should also mention is we really, truly do need you to understand that any clinical questions or questions related to personal situations, such as treatment recommendations, cannot be answered on this forum. We encourage you to discuss these questions with your personal healthcare professional teams. So on that note, I'm going to look at the questions and I'm going to offer some up, and hopefully our doctor will have some answers to this. One of the questions that I found kind of fascinating myself, and I'm curious about your insight on this, doctor, is does more gray matter or lesions mean worse symptoms?
So yes, I mean, the traditional teaching, Corinne, is that MS is a disease of white matter, but that was true when I was a med student, but it's certainly not true now. It's a disease of both gray and white matter. The reason why it was thought that white matter is more involved is that simply there's more inflammation apparent in white matter, and that's probably because there's way more myelin in white matter. But what we now know is that the gray matter, that is where the nerve cells actually live, rather than their wires and connections, is probably as involved in MS as is gray matter. The inflammation is less, but the amount of injury to nerve cells is probably equally prominent. And it's even thought that a lot of the disability that occurs may be actually more due to gray matter involvement than white matter involvement. So it's really a situation, a disease of the entire brain, both gray, white, spinal cord, top of the brain. So it's a pan-brain disease. So it makes it that much more complicated.
Complicated. Yep, that's definitely an understatement, I think. Another question is, somebody is asking if we can expect sometime in the future that there's more research on the infections like EBV that can trigger multiple sclerosis.
Now that's a great question. And, viruses, the viral theory of MS has come and gone, come again and gone again over many, many years, and many, many viruses have been proposed. And it's never been nailed down because many of the viruses that are implicated in MS are very common viruses, like EBV, the one I mentioned, and I could give a whole talk on that because it's actually a very interesting question. I mean, 95% of the world has been infected with EBV, yet EBV seems to be an essential ingredient for developing MS. So what the connection is between very common viruses and the development of MS is unknown. So I completely agree with the person who asked this question. I think there's a very important message here that if you've never had EBV, you cannot get MS. And to me, that's a very important message because for some reason, that virus is a trigger in some patients, for some reason, is a trigger of MS. And yes, I would absolutely agree that more research needs to be done on the connection with that virus and perhaps others and the development of MS. And in fact, that's one thing we are working on, one of the projects I did not have time to tell you about, but we are working on exactly that question. So maybe next year I'll be able to give you some more data information on that. So yeah, 100% agree.
Definitely something to look forward to. All right. Unfortunately, because this has been fascinating, you're giving us such great answers with a lot of information. We're down to our last question. And so I thought this was a great way to end the question and answer period. What do you feel is the most hopeful progress for MS today?
To be honest with you, the most hopeful progress is the following. When I was a med student, we thought we had it all wrapped up. That autoimmunity inflammation is the key. All we have to do is fix autoimmunity inflammation and we've cured MS. To me, the most hopeful progress is the emerging acceptance that we may not have had it right and that the alternate view that I touched upon in my talk actually merits consideration and should be taken seriously. So I think that kind of change in attitude amongst my fellow researchers, the clinicians, the granting agencies, I think is the most hopeful because that's really going to help us push the R&D and our understanding and therefore the therapeutics in a meaningful way, especially for progressive disease. So to me, that's the biggest positive change that I've seen in the last few years.
Wonderful. Oh my gosh. So again, as all great things, we've come to the end of the time for questions. Thank you so much, Dr. Stys. Thank you for your time today. Thank you for participating and for answering our questions and giving us so much information. It's been so helpful. And thank you to everyone for participating today. Again, we appreciate the support of Novartis for making this session possible.